Hi everybody, so in this problem set 61 we're going to be focusing on subsets and then subsets of the set of real numbers. So what you have here at the top is you have three examples of sets, set B, A, and C, and then you have a statement right here, and what that means, this little symbol here, is subset of. And you notice that the statement would be then that B is a subset of A. And all that means is that it contains some of the elements of A. Like 1 and 2 are the set for B, and those are contained within A because A has 1, 2, and 3. So a subset is a set that contains some of the elements of another set. Now, there's another statement down here that A and C are equal sets. A and C are equal sets because they contain exactly the same elements. And another way that you can put that is that A is a subset of C, an improper subset of C. And all an improper subset is that it contains exactly the same elements. So what I like to put here is that equal sets are also known as improper sets, or improper subsets. So what we're going to do with this information, getting a little ahead of myself, another bit of terminology, or notation rather, is these two. This one here is an empty set, meaning that there are no elements within the set, and this one here is a null set. And what's great about this notation is that these can be used interchangeably with this one, the null set, being used most often, meaning nothing is contained within the set. All right, let's talk about real numbers and subsets within real numbers. This is where I get to do a bit of drawing, and I'm going to make sure that I give myself plenty of space, and you should too. Within real numbers, there's a lot of numbers, the real numbers. Now, there's also, believe it or not, a group of numbers called imaginary numbers. You don't have to worry about those until Algebra 2. For now, what most of the numbers that you've been dealing with, probably all of them really, fall into two categories. Of real numbers, there are two broad categories. There are rational numbers, and there are irrational numbers. All right? Now, let's kind of go over and deal with irrational numbers first. Irrational numbers are your numbers that are decimals that don't repeat but go on forever. So you can think of those, pi is one of those, right? You can never tell what the next digit's going to be. That's why there's competitions for people to recite digits of pi. Square root of 2 is another one. That's a decimal that goes on forever but does not repeat. E is another one. That's another one of those special numbers that continues forever. So these irrational numbers, another feature of irrational numbers is that you cannot write them as fractions. You cannot write them as fractions that have integers for numerators and denominators. All right, so that's really the end of the road for rational numbers, or irrational numbers rather. Rational numbers have a lot of subsets. So kind of starting in kind of the most restrictive subset, you have what are called natural numbers or counting numbers. And this is kind of your most, your basic values, and that's 1, 2, 3, etc. Your counting numbers, when you count things. The only difference between natural numbers, which is a subset of whole numbers, is that whole numbers happen to include 0. So whole numbers, subset of whole numbers is natural numbers, and whole numbers include 0, which natural numbers do not. All right, so moving outside of whole numbers lives within a subset of integers. All right, and integers, I'm going to have to put some of them maybe down here. include your negative values. -2, away from negative infinity really, -3, -2, -1, 0, 1, 2, 3, etc. as you keep going up. So there's your integers. So we have natural numbers, which is a subset of whole numbers. Whole numbers are a subset of integers. And then living within the other, outside of the integer realm, are things like 1/2, -7.2, essentially your values that do not fall, I don't want to use the word whole numbers, but are not integers, but kind of fall in between integers. I don't know, 0.58 is another good one. Okay, so this is kind of your family of real numbers. All real numbers fall into two categories of irrational or rational. Within your rational set, you've got natural numbers, which is a subset of whole numbers, which is a subset of integers. Integers is a subset of rational numbers, which is a subset of real numbers. So what we're going to do next with this is we're going to take it and we're going to make some statements about different kinds of real numbers. So take a look on the next page. So here's an example, and the example reads, 1/2 is a set of what real numbers? Well, 1/2, if we look at our little chart there, is a set of rational numbers. And that's really the only set that it falls into, right? It's not an integer, it's not a whole number. Well, if it's not an integer, it can't be a whole number, and it can't be a natural counting number. And it's certainly not an irrational number. 7 is a subset of what real numbers? Well, 7, interestingly enough, falls into the natural number category, right? It's a natural number, but it's also a whole number. If it's a natural number, it is a whole number, right? Which is an integer, which also makes it a rational number. So actually, 7 is a subset of all of these different categories of real numbers. Now we've got one that's maybe a little trickier. 3 times the square root of 2 is a subset of what real numbers? Well, if you do this out, you'll find that actually 3 times the square root of 2 is a repeating decimal, is not a repeating decimal, excuse me. It's a decimal that goes on forever, but it does not repeat itself. So in that way, it only falls into one category of real numbers, which is that it is irrational. One way that I remember this is that, much like irrational people, irrational numbers, you can't predict what's going to happen next. All right, now we get into some fun logic questions. And so we have to say if it's true or false, and then explain why. So here we go. We have a statement here, and the statement is that real numbers are a subset of integers. Well, I have to think about this, and I say, well, okay, are all real numbers integers? That's pretty much what that's saying. And the answer is no. This is actually a false statement, false. And the reason I would say is not all reals are integers. And I can even think of a few examples of real numbers that are not integers, like, I don't know, 1/2 pi, right? There's actually tons of examples, an infinite number. Let's look at the next one. Irrationals are a subset of reals. Well, is it true that all irrational numbers fall into the real number category? Yes, it is. It's true, because if you look back at our little, diagram, we'll find that, in fact, if you're an irrational number, then you are definitely a real number. So I could say all irrationals are real. Now, next we've got irrationals are a subset of rationals. And this is undeniably false, right? In fact, if you are an irrational number, by definition, you are not a rational number. So what we would call that is mutually exclusive. You have to be either one or the other. You can't be both. Mutually exclusive. For D, whole numbers are a subset of natural numbers. Unfortunately, that is false. And the reason for that comes down to one element. It's false because 0 is whole, but not natural. All right, integers are a subset of reals. That is true. And the reason is all integers are real numbers. All right, so there's a set of practice problems where you kind of get challenged with some of these logic problems. And so why don't you take a look at those before you continue.